So we are actually live now, and I'll wait for a minute or two for people to come online. Yes, we already have a few people. Do comment while I'll just share the link with other folks right now. Uh, the Developer Students Club. So today we have a very special topic. It's actually computer vision, and we have a very special guest also. In fact, today's guest is also a DSC lead. He is actually the DSC lead of BPPIMT, which is a BP Poddar School of Management and Technology. So without further ado, I will add him to the stream. Let's welcome him, guys. Hi, Ayush.
Hi, hi, Fazal. Thanks for having me.
How are you?
Yeah, I'm doing great. What about you?
Yeah, I'm doing great too. So now the stage
Uh,
is yours, and I'll take your leave. So
yeah, yes, yeah,
have
sure.
fun.
Yes, yeah. Thank you, Fazal. Yeah. Before I start, I would like to thank DSC HIT for inviting me as a guest speaker, and I'm very much delighted to be here and share my knowledge in computer vision with all of you guys. So yeah, so let me share my screen. Give me a moment. Okay, is my screen visible? Hmm. Okay. Okay, so hello everyone. I'm Ayushman Kumar, and I'm the DSC lead of BPOTA Institute of Management Technology. And the topic for today is introduction to computer vision using Python and OpenCV. So lately, like I am into computer vision for the past 3 years, and lately I'm working on building computer vision algorithms for self-driving cars, in which Fuzzle is also a part of it. So yeah. So moving on. So before we start the session, I would like to tell that you can share your experience about the session on Twitter or LinkedIn, and don't forget to tag Google Devs, Google Students, DSC BPIMT, and DSC Heritage IT, and use the hashtag Google Developer Students Club. Okay, so let's get started. So the content for today's session are as following. So first, we'll go through why computer vision is important, and then we'll see the formal definition of computer vision. Then we will see what is an image, what is a video. Then we'll be learning about few operations and algorithms in computer vision. Then we will apply a particular task in computer vision known as a color segmentation, and then we will do an application which is called the road line detection, using whatever we learned throughout the session. Okay, so this will not be only like the I'll not only be talking about the algorithms, but also we'll be making a simple application using whatever we learned throughout the session. Okay, so this session is less of a theory and more practical, because the time constraint for this session will be around 40 to 50 minutes, and I know that 40 to 50 minutes isn't enough to cover all of the computer vision and all the theories. So I selected a few topics on which I'm going to speak, and I'm sure that you will love this session. Okay, so let's move forward. So the first thing is, why computer vision? So why is it important? Why computer vision? Why you guys should do computer vision in the first place? So first, I would like to tell about how it impacted my life. So in the first year, I learned computer vision, and I went to this competition, IIT Citij, that is the Techno Management Fest at IIT Kharagpur, where we were one of the finalists, where I built me and my team built a bot which uses just a camera to navigate itself around a particular location. It uses purely computer vision. It uses the traditional computer vision algorithms to navigate itself. So you can call it like, a dummy or a toy self-driving car kind of a thing. Okay. And then, yes, the first hackathon that my team won was based on a computer vision application. So yeah, that there also it had a big impact, right? Then I got an internship at DRDO just because of computer vision, and my joining date was somewhere in May or June in 2020. But you know what came and what attacked that thing, right? So uh, a sad thing for me, but it's all right. But it's an experience, and most of us have been through this, so that's not a problem. Okay, continuing. So where is it used? Where is computer vision used? I'll give you a few examples. It is used in a variety of places, variety of spectrum. It has a huge spectrum of places where it is being used. So as to state a few, it is being used in the military equipments, military surveillance systems and everything. And it is heavily being used there for many years. Then it is like popularly used in self-driving cars. You must have heard of Tesla and other self-driving car companies. So they heavily rely on computer vision and cameras. Then it is being used in inventory management systems, like suppose say Amazon Go. It is a departmental store where you don't have to like go and stand in lines to check out and bill the things that you buy. All that happens in the store is that you walk around, you take your items, and there are cameras fixed on the store, and those cameras look at the items, and looking at those items, it gets stored, and and whenever you get home, the bill has been sent to your mobile. So that is good, like, yeah, right. So you don't have to hustle, and you don't have to wait on big lines, which we see in many departmental stores, right? And then it is being like lately used in image in medical image analysis. And yeah, so it is being used for detecting cancer, or it is being used in many medical applications. And then we all know, we all use Instagram, Snapchat, and Facebook, these filters, and it is also a part of computer vision. And the and there are many more applications in which computer vision is being used, and to state every every one of them in this slide, it's not possible, right? And the third reason to learn computer vision is that it's futuristic. Computer vision has that power which can bring the cost of a lot of things very, very low, very affordable. For instance, like 10 years from now, the self-driving car problem was solved using a sensor known as LiDAR, which costs around $70,000 per piece. And now you can solve the self-driving car problem in just a few thousand rupees. So it's a huge uh, difference between $70,000 and a few thousand rupees, right? Um, okay, now we come to the formal definition of computer vision. So what is computer vision? In simpler terms, you can say that computer vision is teaching the computers to gain high-level understanding of from the images and videos. So what do we mean by high-level understanding? So high level understanding means, suppose you look around yourself, right? And you can see that there's a phone or a laptop, right? And you can recognize that, yeah, there is a laptop or there is a phone. For instance, you are on a playground, right? And you see people around you. So you can tell that how many persons are there, and suppose which color of shirt are they wearing, or something like that, right? So these are known as high level understandings, right? So computer vision enables you to like to to computer vision enables you to teach the computer to see how a human sees. Okay. So we will see how it happens in the like all the code examples and for the slides. Moving on. So yeah. So we are talking about gaining high level understanding from images and videos. So what is an image? So first, we are working with images, right? So now when we are working with images, we have to store that image in a particular format, right? So what is an image? So you must have read about data structures known as arrays, right? 2D arrays or matrix. So an image is nothing but a 2D matrix with each cell or pixel having a value between 0 to 255. It has total of 256 values, which ranges from 0 to 255. Any grayscale image is a 2D matrix. You can see this particular background. Wait, you can turn on. You can see this particular image, right? It's an image of Abraham Lincoln, if you can recognize him. Okay, now you can see that there are many pixels here. It is a very low resolution image, so you can see that it's pixelated. Now you can, in this particular image, you can see that every pixel has a number, and every number is between 0 to 255. The lighter the number is, more the value it has. The lower the number is, more darker it is. Okay, now this is how you look at the image. This is how the computer looks at the image, right? Now this is a grayscale image, so this is a 2D matrix. In case of color images, the RGB images, we have a 3D matrix, which is nothing but this 2D matrix, but having three channels. So here is an image which is showing that how it is being placed. So you have the R, you have the G, you have the B channel, and all put together gives you the final image that you see, or the image that you are seeing right now on the live stream. Okay, moving forward. So what is a video? A video is nothing but a series of images played sequentially. So you must have heard about 25 fps, 24 fps, 60 fps on your, like, on your mobile cameras video section, right? So what it is nothing but number of frames being played per second. More the frames per played per second, more smooth is a video, right? So a video is nothing but a series of images. So for the code demo, we will be using Collab. I'll be demonstrating all the code on Collab. Here is the link for the Collab notebook. I'll be sharing this particular slideshow with you, and you will find the Collab notebook attached here. So all the codes been demonstrated during this workshop, you will get it through this particular slideshow. Okay, and so let's get our hands dirty. So let's move directly to the practical part, and through practical demonstration, you will learn about the few theoretical underlying concepts. So let's move on. Okay. Okay, now this is my Collab notebook. Okay, come on. Okay, let me connect my Collab notebook. So people who don't know what is a Collab notebook, it is a Jupyter notebook provided by Google, and it has free GPU for a particular runtime, and you can go and do any machine learning, deep learning, computer vision task here. Okay, so I didn't prefer my particular my desktop for this particular session, because I cannot use the camera, right? Because the camera is being used for the YouTube video. So I thought that, if I do these things on the Collab notebook, it will not only be comfortable for me, but also I can share this particular notebook with you. So yeah. So first of all, if you are doing this on your local machine, then you need to have Python. Of course, you need to know Python before you follow this particular session. Okay, now the first thing what you need to do in order to run OpenCV is that you need to go to your terminal and install OpenCV Python. So for that, you need to go and write pip install OpenCV Python on your command prompt or terminal or PowerShell, whatever you have. Okay, and then once it's done, you can go and import OpenCV. Now suppose If it's not installed properly, then it will throw an error. So for that reason, I have shown here that try import CV2. If there is an import error, then it will throw a message that please install OpenCV Python. For in this case, the Collab already has CV2 or OpenCV library inbuilt in this, so I don't have to install it explicitly. So let me run this cell. To run any cell on Collab, you need just to press Shift plus Enter, and it will be executed. Okay. Now you can see the CV2 has been imported. I can check the version of my OpenCV by using the command cv2 dot underscore underscore version underscore underscore. It will give me. You can see that the version of CV2 I have is 4.1.2. Okay. So the very first task is to know how to read an image, right? We have seen that image is nothing but a 2D matrix or a 2D array, right? Now we have to read that image and we have to confirm it, right? We need to confirm it that whether it is a 2D array or not, whether or if it's a color image, whether it's a 3D array or not, right? So first, for that, we need an image, right? We need to download an image. So I wrote this particular script to download any image by just taking a URL and an image name. So I'm running these two, so this downloads an image for me. And first, to read any image in OpenCV, you need to use the command cv2 dot and its function imread. So imread enables cv2 module to read any image it has. Okay, now this is the directory to that particular image. So test.jpg, as you can see here, it's there in this particular directory. So I just have to write test.jpg here, add to as a string. Now, in case if it was present in a different directory, suppose for say image directory and then a test.jpg, then what I have to do is that I have to mention something like suppose image slash test.jpg. But for this case, I have test.jpg here, so I don't need to do that, right? Now I'm bringing this test.jpg, I'm reading this, and I'm storing this into a variable named image, and then I will see the type of image, right? Now, okay, let's see what's the type of image. So my type of image, my type of img is a numpy nd array, a numpy n-dimensional array, right? So what is an n-dimensional array? It's nothing but a multi-dimensional array. So as I said that image is nothing, the image being read by OpenCV is nothing but a matrix. So you can see that it's a matrix, right? Now you can check its shape like any numpy operation. So if I write img.shape, you can see the shape of the image. So it's 462 cross 780 cross 3. So this is the height and width, or the rows and the columns of the image, and this is the number of channels it has. Okay. Now the image being read by OpenCV is by default in a format known as BGR. It's nothing but blue, green, red. And normally we read that it's RGB. So we need to convert that into RGB in order to just visualize this particular image. Okay. Now for all the matrix operation I'm going to use NumPy. So I import NumPy, and for visualization purposes on Jupyter Notebook or Collab, I'm going to use matplotlib. So I'm going to import matplotlib for that case. In case you don't have matplotlib or it throws some error while importing matplotlib, you can go and install matplotlib by writing pip install matplotlib. Okay, and then you can import it like import matplotlib.pyplot.spld. Okay, now once matplotlib is installed, you can see it's imported. You can go and write plt.imso and that particular variable where you stored your image. Okay, now once I run this, you can see that this is the particular image. But you can see that I said that this particular OpenCV function stores the image as BGR, right? It stores the image as BGR, but you cannot see any difference in this, right? Let me open the original image which I have downloaded. Now you can see the difference between the two. See, you can see these blue patches, right? Look at here. It's actually yellowish and reddish patches, right? So now what we need to do in order to look at the image like this, we need to convert this particular image into RGB in order to just visualize this particular thing on Matplotlib. Okay, so the command for doing that is cv2.cbt color, short form for convert color, and then my particular image, my BGR image, and then comma cv2 dot color underscore bgr to RGB. Now, what this essentially does is that this is the algorithm which converts my BGR image to RGB image. Now, when I run this particular cell, you can see that now you can see it in the same format as you saw when it was opened here, right? When I opened the file explicitly. Cool. Okay. Okay, moving forward. Okay, now this particular function cbt color can be used to transform the image into different color spaces. Now, what are color spaces? Now, color spaces are nothing but different representation of or the formats in which you can represent any particular image. So it is, why do we need like suppose RGB is a color space, HSV is a color space. Similarly, BCR is a color space and grayscale is a color space. Okay. Now, these particular things are used according to the application we want to use it. Suppose for some cases, grayscale image works better than an RGB image. Suppose if you have a high contrasting image, say if there is a black background and a white line, say if there's a white line on in a black background, then you may use a grayscale image because you can visualize it better, right? Because the white thing, like white, it's no use using a 3D matrix instead of a 2D matrix, where you can do your thing in using a 2D matrix. Okay, let's check our image shape. As we have seen that the image shape was 462 cross 780 comma 3. Okay, now like any matrix, we can apply a slicing algorithm. Like you can see this particular thing. So what we are doing is essentially taking the first 200 rows, the first 200 columns, and all the channels. Cool. So this is the sliced image. This was just a proof of concept to show that if you have an image, it's in a n-dimensional array kind of a format, then you can do anything which you can do with an n-dimensional array. Okay. Now you can also like using your matrix operation, your knowledge of NumPy, you can also just visualize a particular channel. You can see that I'm only visualizing the R channel from here. So right now you can see this is the R channel, right? But you cannot see that it's red anywhere, right? But how will you get that? What is the importance of this particular image, right? So you can you cannot get it from like visualizing just a single image, but you will get it when I visualize each and every channel from this particular image. Okay, now you look at this picture. You can see the background. See, the background is bluish, right? And this is the R channel. You cannot see the background. We're having some light intensity or higher intensity values, but if you go to the blue channel, you can see that it has lighter intensities. That means it has more of blue and less of red. Similarly, here you can see that it's reddish, kind of reddish, right? So you can see the intensity here, it's more, whereas here it's darker, right? So it tells that it has more of red and less of blue, right? And same goes for any other color in this particular image. Cool. Now another way to visualize this is through color histograms. So yeah, this particular technique of splitting image I did not use. Instead of this, I used a inbuilt function here which splits your image into 3 channels. So it's not necessary that you do everything explicitly or manually. You have functions on OpenCV which does it for you. So, but it's good to know about how it's good to go in depth and know about what is an image and how everything works. Now let's see what is the type of channels we get. So a channel is nothing but a list of every other matrix. Like it's a list of ND arrays. What are the ND arrays? The R, G, and the B uh, uh, B channels. Okay, let's visualize one of the channels by indexing just by using the list index format, and you can see that it's nothing but an ND array, right? Okay. Now I just wrote this particular function to plot the histogram by splitting the getting all the channels, then just just by calculating the histogram and just plotting it on matplotlib, just a simple uh, matplotlib plot. And you can see that I passed this particular image to this matplotlib thing, and you can see that the color histogram of this, you can see that it shows that number of pixels having these values. Suppose number of pixels having 0, or say somewhere between 0 and 50, it's somewhere close to say 8. So number of pixels having 8 in the red channel is more towards here. So you can say that the picture is like less of reddish and more of blues, right? You can see that the blue is more, right, towards the lighter area. The more light it is, the more intensity it has. So from this particular thing, you can see the picture has more of blue, less of red, and it also has equal amount of green also. Okay, so you can infer many things from this color histogram. When you go into the theories, you will get to learn many applications which you can do using color histograms. Let's move forward. Now we move forward to applying filters. It is also known as kernels. Okay, so what is a filter? Now filters are nothing uh, but a matrix which enhances any particular feature of a image, or it enhances the image in some way. Suppose you have heard of sharpening, right? What is sharpening? It's nothing but applying a particular matrix to your given image, right? Now for here, say I want to find vertical edges. Now this is my image, right? Now you can visualize this image like this. More the value, it's whiter. It's this the value, it's darker, right? And you have this particular matrix, say 1 1 1 0 0 0 minus 1 minus 1 minus 1. You can visualize this particular matrix as white, gray, and black. And what we do is that we slide this particular matrix over here, and then we store the resultant value here. So what essentially happens is, let me share the code, the Colab, the slides again. Um, Let me share the entire screen. Okay. So what happens is that uh, essentially you have this particular matrix, right? And it slides over your original image. And when it slides, it multiplies each and every element with the portion on which the matrix is already present, and then it adds up the whole matrix. Okay, now when it adds up the whole matrix, it is then stored in a different image. This is nothing but applying a filter. In OpenCV, you can apply a filter just by using a cv2.filter2d function. And and filters are also known as kernels, as I've said. So let's again move to the code example. Now this is the image, and now you have this filter, and then you can apply this filter, and you get this as a result, where you can see that this defines a edge. Okay, you can see that it can define an edge, right? Now on a bigger perspective, let's do this operation on our particular image. Now I have this particular vertical edge filter. Why we are calling this a vertical edge filter? You can visualize that it has a contrasting feature. from say white to a lighter set to a darker set. You can see that it's contrasting, right? Now this contrasting filter is being slided over this particular image, and it will give you the vertical edges. Let's go and visualize this. Let's see what's the result from this particular function. So you can see that from this particular image, you have got all the vertical edges which is possible to extract from this particular image, right? And these are the vertical edges, right? You don't get any horizontal edges here. You only get the vertical edges, right? And these edges can be useful in many cases. Suppose if you if it can be it has many real world applications. Say if you have something sort of a lines on your straight lines on your say on if you have a task, say, and it has multiple lines and you have to count the lines, say you can apply a vertical edge filter, and you can find that what are the number of lines there. Like it's possible, and it has many more applications. Let's not discuss every one of them, because if I go into those things, then I cannot complete this particular session. Okay, now we come to horizontal edges. So its horizontal edges are nothing but just transpose of the vertical edge filter. You can see now every row has -1, and every row has 0 and 1. So I've just transposed this particular my initial kernel, and now if I run this, I'll get all the horizontal edges possible from this particular image. Now you can see that curl sitting on a sling. You can see that sling, or the tree where it was hung, like those kind of features. Okay. Now there are many kinds of filters. Just to state a few, there are blur filters, sharpening filters, and there are endless kind of filters which you can go and experiment with. Okay. Now just to demonstrate, I demonstrated a few filters here. Now this is the blur filter. So this does nothing but blurs your image a bit. You know what blur is, right? Um, okay, so this is the blur filter, and okay, now you did this manually by writing these kernels. Now it's good to know how to do it manually, but OpenCV already gives you functions which applies it for you, like better than what you can apply using these filters, and it's faster than what you apply here. But it's good to have the knowledge about how it's done. Um, Okay. Now, so the algorithms which OpenCV gives you are popularly are Sobel filters or canny edge detection. So here I'm going to demonstrate canny edge detection. So for applying that, you have to use the function cv2.canny to get that. So what I essentially do is that I write cv2.canny. I give my initial image, and then I have some threshold values. I won't be discussing what these values exactly mean, but you can play around with these values and get different edges according to different situations. These are basically hyperparameters which you can use to according to your particular situation. So these parameters can vary from situation to situation. For this particular demo, I just randomly picked some hyperparameters, and let's see what the results are. You can see that how good the edge filtering is being done, and how good the results we have got, right? And it has all kinds of edges incorporated, not just vertical or horizontal edges, but all kinds of edges. So canny algorithm is a superior algorithm compared to what we did uh, on the top. Okay. Same goes for the blurring algorithm. You have the Gaussian blur algorithm, and you have this you give the input image, and then the filter size is nothing but it's comparable to, this was a 3x3 filter. You can now the Gaussian blur, I'm applying a 5x5 filter, and 0 means the amount of blur I'm putting, right? If it's 0, then it's a slight blur. If it's 1, then it's more. two more, right, like that. Okay, so let's apply the Gaussian blur. So it's simple. It's simpler. You don't have to, instead of writing five to six lines of code, it can be done in just a single line. Okay. Now let's. So the filtering part is over. Let's now move on to color filtering. Okay. Now color filtering. So for that, I'm going to download a different image. So I downloaded a different image. Okay, now let's see what the different image is. So I'm reading that particular image. Okay, now I'm converting that into RGB from BGR just for visualization purposes. So you can see that this is a wonderful image of a Coca-Cola can placed on this rock, and it has a good background kind of a thing. Okay, and so you have this image, and now what I want to do is that I want to filter this Coca-Cola out of this image just by using the color information which I have. Okay, so for that, what I need to do is that I have to go to a different color space, because it gives me more I can say it gives me more uh, uniformity while choosing the colors. Okay, now from RGB we will move to HSV, which stands for hue, saturation, and value. Value is nothing but you can call it, you can understand it as lightness. Hue gives you the detail of the colors, and saturation is that how dark, and the basic English meaning of saturation, right? So yeah, so hue, if you change the hue, you will get different colors, as you can see in this image, right? So what we do here is that we convert our initial image into HSV color space using the CVT color function, and you can see that you get this gibberish alien type of of outcome from this particular filtering. Okay, this color space. Okay, but it's important for us because this will be used for filtering out this Coca-Cola bottle, this Coca-Cola can. Okay. Now what we need to do is that we need to provide it some range, right? Now suppose for RGB you have the RGB color codes. So for RGB you can say that R corresponds to the first value, B corresponds to the second value, and G corresponds to the third value. So suppose if I give 255,0,0, it means red, pure red in the RGB color space. So similarly, in the HSV color space, you have red in this particular value, and also you have red in this particular values, because there are many kinds of reds, right? Like it's not just a particular red, but you have cherry red, or there are 100 kinds of reds, right? So you need to provide it a particular range, right, or in which your particular specific color is lying. So I provided it with two kinds of color ranges, and what I do, I will just filter out those colors from this particular cola can. Okay, from this particular image. So I'll be using a function known as cv2.endRange, and I will provide my Cola HSV, which is nothing but the HSV image. Okay, and I will provide it my two upper bound and lower bound reds, and then so what it will do is that it will filter out just the red part from the image in this particular color spectrum. Okay, now this what you can do is, suppose if you if you apply these particular values and you don't get a satisfying result, what you can do is that you can again you can tweak these values for a better result. Okay, um, so I didn't experiment much with these values, and I'm just showing what I got out of these values. So this is the result which I got, is nothing but the spectrum of the red range which I gave it, and you can see the value. The output is not that bad, but yeah, there are errors, and we need to correct these errors while working on any particular application. So again, now we got this mask, right? Now out of this mask, we need to like if we need to visualize it in a better way. For that, I'm using a bitwise OR operator. It's nothing but it's comparable to what you read in your digital electronics or your digital electronics class, right? Like what's OR, like 1 or 0, it gives 1. 0 or 0 gives 0. 1 or 1 gives 1. 0 or 1 gives 1. So it's nothing but that. Here where the mask, the white portions is 1 and black is 0. So I give it the my RGB image, and I provide my mask as this particular image. So where the image will find 1, you can see red, else you will find nothing but black. Okay, now let me run this image or run this function. Now you can see that you have the red color, but still you can see that there are many problems with this particular filtering. Now this can be corrected using few image processing techniques. Now for that, let's see a application of the few filters which you read, which we have seen earlier. So first we are using Gaussian filter. Okay, the Gaussian blur. What Gaussian blur does is that it just not blurs the image, but it also makes the image smoother. When something is blurred, it is smoother than what you have initially, right? So I'm applying a blurring filter to the mask which I have. So the it corrects the mask to some extent. It might not be the best results, but it's obviously better than what we had on the top. You can see what's the difference between the two. It has less of noise, right? Now it's not enough. Like you can see, the Gaussian blur is not enough. So what we do is that we apply a different algorithm known as dilate or dilation. What it does is that it tries to expand. It's try to expand, your mask to a certain bit, such that if you have some noises on the edges, it will get removed. So you can see that you can treat these as noise, right? You can treat these as noise. So let's apply a dilation algorithm on our Gaussian blur mask, and let's see what the results are. You can see that there are more white portions here, right? You have more of white portions here, and the noise is being removed to a greater extent than it was done on Gaussian blur. Now you can compare this particular image with, say, this one. So you can see it's better than what we had, right? It's better than what we got initially. You can also, like, for this particular dilate algorithm, what we need to do is that again I am defining a kernel, say your np dot ones of 5 cross 5 5 cross 5, and you just need to provide your mask, your kernel, and then iterations is equal to something. The more the iterations are, the more times the kernel will be applied. So I'm keeping it as 1 because I don't want to like overdo on this particular task. So you got this result. Now suppose if I wanted to just experiment with my kernel size, so I applied 3 comma 3 3 cross 3, and everything remains the same. So you get this result. Both of them are like have a few differences, yet I in the next cell, I have used this, but the latest results, okay, for visualizing. So now we have the corrected mask of this particular image, and now again we are using the bitwise OR, and let's see what the color mask is. Now you can see that the color mask is far more better than what we got here, right? Right, you can see the difference, you can feel the difference between the two, right? And it's all possible by applying some post processing techniques on your particular initial masks. Okay, now it's done. Now let's move on to the application, and in this particular application, it will be a road line segmentation or road line detection algorithm, just by using whatever you have learned, what we have gone through in this particular session. Okay, so for that, I'm again downloading a different image, and again it's called road.jpg, and let's visualize it. So this is the road image which I am using here. You can see that there are lines, right? There are lines and there is a road. What we need to do is that we need to detect these lines on the road. Okay. Now for any self-driving car, these lines are really important for like localizing and navigating the car and navigating the car on the road. So yeah, so this will be just a toy demonstration of that particular thing. You can also do it's simple. It's not that hard to like get started with. Okay, the first thing is that you can see that there is a high contrast between the road and the white lines, right? These are dark, these are, and this is very much light, right? So what I do is that first I'm converting my uh, color space from RGB or BGR to gray. Okay, now you can see I converted my image to gray. Okay, now what I will do is that I will do something known as a thresholding. Uh, the spelling is wrong. It's HOLD. Okay, ignore my typos. Okay, what thresholding does is that it converts your image into a binary image. So what is a binary image? This can be treated as a binary image where you have only two values, 0 or 255, or if you normalize these terms, you can say 0 or 1. Okay. Okay. Now, yeah. So what thresholding does is that it converts your image to a binary image. So what it takes the initial grayscale or any image you provide it. Then it takes the two values on the values on which it is going to judge it. Okay. Now I I chose 230 to be my boundary, my threshold value. Okay, and 255. So it will be ignoring everything which is less than 230. Okay, for this particular thing, and it is using an inbuilt function known as trace binary. It's nothing but white will be remaining white and other rest will be black. Okay, now let's see what the results are of this binary image, and you can see that you have you can clearly see the road lines on this particular image, right? You can see these road lines on this particular image, and now we have read about the Canny-East filter. Okay, now I'm applying this Canny-East filter to this particular thresholded image, and you can see how beautifully it has found all the edges. Now you can see that there are noises on these edges, right? Now to better my what I can do is that I can smooth out my threshold image. So for that, as we have done earlier, we will be using the Gaussian blur. Again, the Gaussian blur smooths your image to a certain extent, and then again we are applying our Canny Edge filter. As we apply our Canny Edge filter, you can see that you can feel the difference between the two. See, it's smoother than what we initially got here, right? There are noises, there are many noises here, but here it's far more better than what we had. Okay, so now once we have this particular edge map, now we can use an inbuilt function. It's called the Hoffline P function. It's popularly known as the Hoff transform. The theory is there available on the internet. I'll provide you the books and links from which where you can go and read the theories. And for here, you can use these algorithms. So what this algorithm essentially does is that it takes the edge map, and from these edge map it finds all the lines present in this particular edge map. Okay, and then once I get all the lines, I loop over the lines, and then I use the function cv2.line, which does nothing but draws the line on my image. And I have my x1, y1, x2, y2, basically the endpoints of the line, the end coordinates of the line, and I have my image, and then I have uh, these coordinates, and then I provide the color of the lines which I want to use. So here it's PGR. For G it's 255, error is 0, so the lines will be green, and 4 is nothing but the thickness of the lines which I'm going to get. Okay, I apply my algorithm, and do uh, and I see visualize my results, well, you can see that you are getting perfectly here, right? You're getting perfectly the line. You're perfectly detecting the lines on the image, but you are getting some noises here. You are getting some unnecessary dummy values here, right? Because kind of it also the algorithms also detects these things as lines, which is not good, right? So what we can do essentially here is that we can, like, suppose I said that this is a matrix, right? This is a matrix. So what I can do is that I can apply my particular algorithm only up to this particular space and not on the top, right? For that, what I can do is that I can just slice out. You can see that the shape of this road is that the shape of this image is 183, 275, 3. So 183 are the number of rows, right? The number of rows. What I do is that I will apply a threshold value of 100, and now all the lines which I detect right now will be detected only on this particular region. Okay, so you have this particular image. You can see that I have created a copy of the original image here. So RGB2. Okay, and so what I'm going to do is that I'm going to run this function, or you can see that I have applied. I have sliced the original image. I've sliced the edge map, and then I have applied that to the image, and then I have transposed the coordinates to 100 because I have applied the edge maps. I've sliced the edge map in that fashion. So just to adjust the height of the detection. You can see that the edges are only being seen on the road lines. Okay, now this was the code demo. So what we have essentially learned through this code demo is that uh, first, how to read an image on OpenCV, how we can visualize different channels across an image, what is the use of color histogram and how you can get color histograms, the knowledge of filters. You can experiment your own custom filters to detect some funny thing or maybe some important things from your image. You can go and experiment around with it. And then we learned about various inbuilt functions which does this work for you. And then we learned about color filtering. We learned about smoothing images and denoising an image. And then whatever we learned on the top, then applying those things, we did a very simple lane detection algorithm. Okay, so let's move forward. So yeah, so I would like to suggest a book if you want to go into the theories, if you want to like pursue computer vision as your career option, or if you want to like get into the deep well of computer vision. I found this but with this amazing book which is available for free. The free samples are available on this particular in this particular link. So it's by Richard Zaleski. I pardon for my wrong pronunciation, but yeah. So he is only distributing the samples of this book. You can go and download the sample of this book from this particular link. Now, this is an amazing book which covers wide ranges of computer vision algorithms using traditional and deep learning methods, both the modern and the traditional algorithms. So you can go and check it out for sure. Okay. For code examples, you can go to the OpenCV documentation. It's amazing. It covers wide ranges of applications which you can do using OpenCV, and there are many good code examples which you can follow and learn OpenCV by your own. Okay. Now, if there's any question, then I'm open to any question. Okay. Is hit and trial the only option to segment the object based on the color info? Okay. Only hit and trial. Yeah, you may like you can use hit and trial. Like, see, the traditional algorithms, it's very chaotic. The traditional algorithm, the real world is very chaotic. Okay, now since the real world is so chaotic, so a particular value cannot be used at every situation. Okay, so yeah, for that, if suppose you have a control situation, or you have control lighting and everything, then you need to tune it like you do with anything, right? Suppose if you are a musician and you have to tune your you have various knobs on your music system, right? And you have to tune those knobs to get the ideal sound you want. But then this, you can compare this to this particular hyperparameter equalization, this hyperparameter optimization. Okay, what are some ways to deploy for showcasing our projects, our OpenCV project? Okay, now OpenCV is available for Java, for Android development. It is also available for in the form of OpenCV JS, and it's also there for in Python, of course. And before Python, it was there for C++. So you can just you can, if you have the knowledge of say Android development using Java, then you can very much go and use OpenCV there, and you can apply. You have many resources available on the internet which you can go and follow for sure. Okay, and that's the only. Those are the only questions. If anyone has any other questions, then you can put your questions here. Um, okay, so okay then. Thank you. These are my coordinates. You can go and find me here. Uh, you can follow me on GitHub, Twitter, LinkedIn, and thank you.
Hey,
Hi,
Ayushman.
Fazil.
Yeah, it was a really great session. It was
Yeah,
really
thank
nice
you.
and amazing. Uh, Guys, just so you know, in the last minute, he was giving you so many comparison of tuning. In his free time, he plays the guitar a lot. You can check it out on the YouTube and Reels. So that is why he
Sure,
was
sure.
making so much comparison between the um, musical instrument. And so yeah, if you have enjoyed the session, post session I will be sharing all the links, the slide links he will be providing me, and I'll put it in the Telegram group, the official one. So no worries. So Ayushman,
Yeah, Fazil. Okay, then
okay then,
it
bye.
was it was a great experience. Thank you,
Yeah,
Fazil, for
yeah,
having
you're
me here,
welcome. You're
and thank
welcome.
you, the DSC team. Uh, okay,
They're glad to
okay.
have you.
Bye.
They're all glad to have you.
Thank you,
Okay,
Fazil.
bye.
Thank you everyone for having me here. Okay, tada.